Hello class, Professor Anderson here. Let's talk in general terms about conservation of momentum. What we said last time was Newton's third tells us that there are equal and opposite forces between objects. Okay? No isolated force exists. You always have equal and opposite forces. This is the action-reaction law, right? For every action, there's a reaction. And what that led to is conservation of momentum. Momentum we're writing with a P. For some reason, we've run out of letters again, right? M got used up by mass, so momentum we're using P. Okay? It's a direct result from Newton's third law. Start at Newton's third, you can get to conservation of momentum. But what do we mean by momentum? Well, momentum is mv. That's the definition of momentum. It's the mass times the velocity. It is a vector, okay, which means it has components. P sub x is m, v sub x, P sub y is m v sub y. Okay. It has vector components. Now, anybody have any problem with what I just wrote? I'll give you a hint. You probably should have a problem with what I just wrote. Kevin? Joseph, can you hand it back to Kevin?
You wrote components on the mass term?
Yeah, why would I write components on the mass term? Is the mass a vector or is the mass a scalar?
It's a scalar?
It's a scalar, so there should be no components on the mass term because it's just a number. It's 5 kilograms, it's 10 kilograms, it's just a number. No components on the mass term, okay? Components go on the velocity, right? The velocity has components to it. So, what does conservation of momentum tell us? It tells us that P initial equals P final. And this is really important to understand everything that's in this equation. There's kind of a lot that's in this equation. This is the system's momentum initially. And that is equal to the system's momentum finally. Okay, you have to be able to identify the system. So in the example that we just talked about with a rocket exploding into 3 pieces, you can put a dashed line around that rocket and that will define the system. But let's ask a question of you guys. Okay, here's Newton's apple. Okay, Newton's apple fell from the tree and supposedly hit Newton on the head and he went, oh, what's going on, right? And he thought about it. We know what's going to happen if I drop this. It's going to fall. Okay, gravity is pulling it down. Is the momentum of this apple conserved here? As soon as it leaves my hand, and when it comes back to my hand, is the momentum conserved? Let me ask you guys. Raise your hand if you think the momentum is conserved in that simple experiment that I just did. Okay? About half of you. Raise your hand if you think it is not conserved. Okay, one of you. A half plus 1 equals. All right, the answer is it's not conserved. The momentum of the apple is not conserved. Why? Because when I threw the apple up, it was going in the positive y direction. But when it came back down, it was going the opposite direction. There was a minus sign. Momentum of the apple was not conserved. And yet, this whole section is about conservation of momentum. So what are we missing here? What are we missing in this experiment? Megan, you want to pass the mic over to Megan? Okay, while you're getting ready for your question, I'll do the demonstration again. I know it's very
Okay.
complicated.
Okay, I'm not 100% positive, but I think it's because when the apple leaves the hand, you're no longer factoring in the entire system.
Okay.
Because isn't your hand part of the system?
Well, my
Can you throw
hands,
it?
my hands may be part of the system, but as soon as I let go of the apple, I can just keep my hand stationary, right? And then I'll catch it again.
Okay.
So the hand could be basically velocity 0, so maybe that's not really part of the system, but is something else part of the system?
Gravity
Gravity due to what?
due to... I don't know. I don't...
Okay,
Not
well,
sure.
there's something that's pulling this apple down. It's the same thing that's pulling you down,
Weight and gravity.
right? And what is gravity on this planet due to?
Weight
It's due
Mass.
to the mass of what?
of the object.
Of the
apple.
object, but it's being pulled on by the
The
mass
Earth.
of the Earth. The Earth is part of the system.
Oh.
The apple is not the system. The system is the Earth-apple combination. All right, so that's kind of weird to think about, right? But the idea is you have to identify the system, and you can't have any forces that are crossing across your dashed line. So let's draw the picture. Here's the Earth. And here's the apple. Okay, got a little mangled. The apple is falling. If I draw a dashed line around this to identify the apple as my system, are there any force lines that are crossing across that dashed line? Yes. Gravity, Fg, is crossing that system line. And so that cannot be our system. If there's any force lines that are crossing your dashed line that you just drew, that's not the system. You have to draw a dashed line such that no forces are crossing that line, and therefore the system is really that.
So hypothetically, if you threw the apple hard enough that it left our atmosphere, would you then be breaking the rules because you're taking it out of its system
Okay.
as far as conservation of momentum goes?
All right, that's an excellent question. Let's say I throw that apple up so high that it's sitting way up here. Here's my apple. Okay, and it's outside the Earth's atmosphere. Are there forces that are acting on the apple?
Yes.
What?
A little bit of gravity.
A little bit of gravity, right? It's maybe smaller, we'll put a prime on it, it's something less, but there's still a force acting on it. So now your system envelops everything again, the Earth-apple system. It's around the whole thing. I mean, just because you get out of the atmosphere doesn't mean gravity turns off, right? It just means there's no more air, but gravity's still acting on it. That's why the moon stays in its orbit, or the International Space Station stays in its orbit. Okay, so you still have to include everything. So let's go back to this simple problem for a second. Okay, if this is the system, and now I'm holding the apple like this, and you're looking at the apple-Earth system, what is the momentum of that system right now? What's your name? Emilio. Okay, Emilio, what's the momentum of the apple-Earth system right now?
0?
0, because the Earth isn't moving, the apple's not moving, everything's stationary, right? Velocity 0. So now, when I throw it up, and it's on its way up, what is the momentum of the apple-Earth system? What do you think, Emilio? I'll give you a hint. Conservation of momentum. If you started with 0, what does it have to be from there on out?
0?
0. the apple on the way up, the momentum of the system is still 0. But it doesn't make sense, right? The apple's going up. Shouldn't that be like some sort, oh, I bruised my apple. Shouldn't that be some sort of positive momentum? What does that mean is happening to the earth, Emilio? If the apple's going up, right? If this is our apple and it's heading up right after I throw it, what does the earth have to be doing?
Pulling it down?
Has to be going down. The earth itself is actually going down. And now when the apple is coming back down, what's the earth doing, Emilio?
Exerting a force on the apple, basically, but I mean, pulling
Okay.
it.
We just flip the directions of the arrows. If the apple's coming back down, the earth is going back up. And so this is really weird to think about, right? But if my fist is the earth and here's the apple, what they do when I toss it is this. And then I catch it again. That's what happens, right? Which is kind of weird to think about. It goes like this, and then it comes back together, and then I catch it and everything comes to a stop. And the momentum of that whole system is 0 the whole time. Now, the earth is pretty massive, right? So it doesn't move very far. It doesn't have a lot of velocity, but it has the exact same momentum as the apple. M times v, since m for the earth is huge, the velocity can be small. Okay? So inherent in this thing that we just talked about is the notion of an isolated system. You have to draw a dashed line around your system such that no forces cross that dashed line. And that's sort of step 1 in identifying these problems. Yeah, Joseph. Can you hand the mic to Joseph real quick?
If that's the case, where if you have any forces on it, it has to be included within the system, would that mean that, what about like forces like you were saying before, like the moon or the sun's gravitational force on us, would that be included in the system whenever you're using any physics properties?
Okay, technically, yes, right? Technically, if we said this is our isolated system, that's not quite right, because you still have the moon out there. The moon is pulling on the apple. The moon is pulling on the earth. You got the sun over here. The sun is pulling on the earth. The sun is pulling on the apple. So specifically, you're right. We don't really have an isolated system. This is an approximation to an isolated system because the moon's pull is pretty weak compared to the pull of the earth. The sun's pull on the apple is pretty weak compared to the pull of the earth.
So does that mean when we do something, there's an opposite force to those gravities, it's just not really recognizable?
So when I throw this thing up in the air, I'm applying a force to get it going, which pushes me and the earth down. And when it comes back down, that is gravity acting on it. That's pulling the earth back up and it down. And when it comes back into my hand, there's a force that my hand applies on the apple, and now everything comes back to rest. So the system sort of goes like this, and then comes back to rest. And during that interaction, Newton's third tells us that all forces are equal and opposite. If there's gravity on the apple is exerting gravity on the earth. If there is a force of my hand on the apple, there is a force of the apple on my hand, which is pushing me down. Yeah. So, simple concept, very confusing ramifications of it, which I think is kind of cool.
What if you blew up the apple?
What if we blew up the apple?
Yeah.
Then
While
we-
it's in the system with the earth. How would that affect the earth?
Okay. I like that question. I think any sort of questions where we get to blow stuff up, those are good questions.
Demonstration would be cooler, but
Anybody bring a firecracker? Yeah, so if you have an explosion, momentum is conserved. Okay, so it doesn't really matter when that explosion happens. If I put a firecracker in this apple and I throw it up in the air and it explodes in midair, and let's say it goes into two pieces, right? One that goes up and one that goes down. The momentum of the entire system still has to be conserved. The apple parts combined with the earth, that whole system, the momentum still has to be conserved. Okay? So there's some fantastic videos on YouTube. One by a group called the Slow-Mo guys. Have you guys seen any of their stuff?
Yeah.
All right, so they have these high-speed cameras and they like to blow things up a lot. So one of the videos is them blowing up a watermelon, and they put, I mean, it looked like, you know, a half stick of dynamite in this thing. It was probably like an M80, but this thing just obliterates. And what's interesting about that is, well, what I thought was interesting was, one, the guy sitting there without wearing safety goggles, which I thought was a little ridiculous. But two, the shrapnel basically goes in every direction nearly uniformly. So if I think about a sphere, and I put an explosive device right in the center of the sphere, and it's going to blow apart into a whole bunch of little fragments, all of those fragments are going to go equally spaced in every direction. Okay? They're all going to go out radially, and it's basically like you've blown up the entire watermelon in some uniform distribution. So as you get to more and more parts that you're exploding, everything is going to go out with essentially the same direction, radial, and similar velocities. It's going to conserve momentum of the whole system, of course, but it's going to go out uniformly.